All right. Hello and welcome to the last lecture of ME3331, the thermodynamics class. Today I'm going to be finishing up chapter 10, and that will be all we have done for this class. So we've taken this class all the way from the very beginnings of looking at thermodynamic principles like work and heat and energy, and applied them to individual processes and control volumes, and then moved into cycles. And the last bit of time we've looked at some gas cycles, some power cycles, some vapor power cycles, and now we're looking at some vapor refrigeration cycles. And at the very end, we're going to do a gas refrigeration cycle based on the Brayton cycle, which is something we also learned. So that's about it. And so with regards to the final exam, some of you may be wondering about that. Final exam will be given when the normal final exam is. I believe that's this coming Saturday at 4 o'clock in the afternoon. And it's marked on the calendar in the Canvas page. Let me just make sure that it's there while we're here all here together. Let's see, final exam, yes, 4 o'clock. Of course, there's nothing here. I don't know why that is there, but okay, so 4 p.m. There is a, this is my office hours. I will be holding this office hours on Wednesday the 13th, by the way. Semester's still going on, and I'll answer anybody's questions about the final exam, etc. But Saturday the 9th at 4 p.m. is the final. The final exam will be the same as the second midterm in terms of its format. So I'll be putting out there an open book exam. You can do it using the using this, all the resources that you have, except each other, and you'll have 2 hours to complete that exam. Okay, and then turn it back into Canvas. I may allow a little extra time for turning things back in. I will try not to make the exam as difficult or tricky as the second midterm, but it's not going to be easy. Okay, don't expect an easy exam. I'm gonna try to keep it fair. Okay, and of course I will curve the exam if I need to, so don't worry about that. If you have any questions, please write me an email and ask me, or you can contact me during my office hours this week. Okay, so yeah, as I said, this is our last lecture. This is the second to last third survey I'm looking at. The survey, again, there will be a survey tomorrow. That is Monday for this class, and do as usual. So looking at this survey was the capacity of a vapor refrigeration system is, pick one. So heat flow out of the condenser, no, that's not it. Heat flow out of the condenser is not right. That's in the high temperature place, so the capacity is not how much heat we're ejecting to the ambient. Power into the compressor, no, it would make sense. I would think if there's anything that you might be tricked by, it's the power into the compressor, because that's the amount of power you pay for. So that's sort of the capacity, like how much electricity you'll need to run this thing. But that was wrong. This one, the workflow out of the valve. So first of all, valves have no work, right? We all know that they're isenthalpic, meaning they're H1 equals H2. So whoever chose this one was either messing around or really is very lost, or just picked it randomly, because there's no work from a valve. So the right answer here, most people got heat flow into the evaporator. So that's the cold side, the QC. Okay. All right. There'll be one more survey, as I said, tomorrow, and that'll be it. I think these worked out pretty well. It gives me a good gauge of how people are doing and what people are understanding with the material, if they're understanding anything with the material. Okay, let's see. Where are we at? Okay, here we go. So I am going to go to the slides now. So the slides, so I've updated the slides. I had absorption refrigeration cycle in there, but I decided to get rid of it because it's too complex for us right now. We didn't do any mixing or anything like that, and there's no analysis that we can do. So I threw in some gas refrigeration cycles, which we can get to at the end if we have to, okay? Or if we have time, rather. All right, so vapor compression heat pump system. So the objective of the heat pump is, well, maintain the temperature of a space or industrial building or whatever above the temperature of its surroundings. So it's a heater, okay? So you think, well, the easiest way to have a heater is just like fire up a gas burner or a resistance heater and just heat the space. Well, in some cases, you don't have that high temperature source. You've got electricity. Okay, so you got electricity, and you can power a compressor. And so you can run the vapor refrigeration cycle backwards. Well, not backwards. It's the same direction. But instead of having the QC and the QH where they are, you're taking the heat out of the condenser and you're putting heat into the evaporator. Okay, in the normal house, this would, well, normal house, a normal system that you might have in your house, like I have in my house. This is the condenser out here, and this is the evaporator in here. In the case of a heat pump cycle, they're swapped. So the condenser and evaporator are different sides, and you take the heat off the high temperature side and into the cold, from the cold air outside. Okay, so it's the same components as a vapor refrigeration cycle. That's why I thought it'd be interesting for us to analyze it. So the performance parameters of this are, first you have what's called gamma, which is the coefficient of performance. It's the same idea as coefficient of performance of a refrigeration cycle, except that here we're talking about what Q out is, not the QH going out into the high temperature space, not the QC, which is the heat from the evaporator. Okay, so it's the heat from the condenser that we're interested in a vapor compression cycle. Okay, Carnot efficiency, Carnot coefficient of performance. This is just looking at the maximum possible coefficient of performance we have, which is TH over TH over minus TC, which we'll do a little comparison in our example today. This equation represents the maximum theoretical coefficient of performance of any heat pump cycle operating between cold and hot regions, TH and TC. So if we have an ambient outside and we have a desired inside, we know what the maximum coefficient of performance can be. So we will do that. All right, so this is just an example here. Method of analysis closely parallels that for vapor compression refrigeration cycles. So closely parallels. It's exactly the same, except for the coefficient performance is a different thing. So a vapor compression heat pump cycle with R134A as a working fluid maintains the building at 20 C when the outside temperature is 5 degrees C. The refrigerant outside, the refrigerant mass flow rate is 0.086 kilograms per second. An additional steady state operating data are provided in the table. Okay, so here's some data for states 1, 2, and 3. There's the H's. Determine the compressor power, heat transfer rate to the building, and the alpha, the coefficient of performance. Okay, so here's the building and blah, blah, blah. You have 5 degrees C outside and 20 degrees C inside. Okay, so the compressor power is given by the same as what we had before. So there's no heat, right? So we always assume that the compressor in the turbine in the case of the Brayton cycle and the turbine in the case of the Rankine cycle are all adiabatic. That doesn't mean that we assume that they're isentropic. That means we always assume they're adiabatic. In this case, so WC, this WC dot, which is the power into the compressor, equals m dot times H2 minus H1. Worked out of the compressor then, if you just take the values there from the table here, you have the mass flow and you have the change in enthalpy, gives you 2.4 kilowatts as the answer. The heat transfer provided to the building is the Q out, right? So and the heat Q out coming out of the condenser, which then equals there's no work because of the heat exchanger. So it's H2 minus H3, which ends up getting 15.4 kilowatts. Now, if you were to calculate the coefficient of performance, you'd see that the coefficient of performance is something like 6.4. So, 6.4 is what when you have getting a heat pump. And the maximum theoretical coefficient of performance of any heat pump cycle up between hot and cold, respectively, is 19.5. Now, one thing to notice is that if you desire a certain TH, and this isn't plotted here, but I'm just going to put this in. So if you desire a certain TH, like, I don't know, 20 degrees C, right? And your TC is cold, like getting colder and colder. So what happens, just think of it as a thought exercise right now in your mind. What happens when TC gets smaller and smaller and smaller and TH stays the same? Think about it. Okay, denominator is getting bigger and bigger and bigger, right? So as the denominator gets bigger, what happens to the coefficient of performance? Right, it goes down, 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 right? So what happens is, if you end up getting a heat pump in Minnesota that operates between, say, 5 degrees C, but maybe like not 5 degrees C, but I don't know, -5 degrees C or negative. I mean, look, -5 degrees C is nothing for Minnesota. Say -10 degrees C, right? So say you have -10 degrees C. I'm just going to use my calculator here, that I can never seem to get the numbers right. But essentially, if we send that difference is between 293 minus what did I say, 278. So if we have 5 degrees C, so if we're down another, I don't know, say 268, which would be -5. So let's say 262 or 263. 293 minus 263. 293 minus 263. Just 30, right? So now you have a 30 on the bottom. So 293 divided by 30 ends up getting coefficient of performance of 9.7, ideal. So what happens is as you get colder and colder, right? And 20 degrees C is not very hot, right? I mean, usually when you're cooking in your car, you want to turn it up to like 80. So then you're getting even higher, your TH gets even higher, and then your denominator. So what happens is that the coefficient of performance starts getting lower and lower. The ideal and the actual is like some factor below that. So what happens is you end up getting very poor performance as the difference as the denominator gets bigger and bigger, and it's better just to burn something and heat it as opposed to using a vapor compression cycle. However, if the difference is very small, between 20 and 5 degrees C, for instance, you get a very decent coefficient of performance. 6.4 is pretty good, and the ideal is like 20. So, I mean, it's pretty good. You could get away with that. So when you're in a place like Florida or a place like South Carolina or something that has some cold nights, or Texas that has some cold nights, heat pump works fine. Then you already have the hardware. You don't have to have a furnace. But in Minnesota, when we have really cold winters and you want to keep your place nice and toasty, heat pump's not going to do it. It's just not going to do it. Okay. Anyways, let's do an example ourselves. So let's do, I think that's next. Yeah. Okay. My example for the day. Actually, I have two examples for the day if we can get through them. Let me just get here. All right. So here's my example for the day. So the figure and table give data for an ideal vapor compression heat pump cycle operating at steady state with R134A, like the previous example, as a working flow. The heat pump provides heating at a rate of 15 kilowatts to maintain the interior of the building at 20 degrees C when the outside temperature is 5. Okay, so this is like the exact same thing we just did. Oh, are those the exact same parameters that we have in the example? Well, it doesn't matter because we're going to write them out and you're going to see how it's done, and it's going to be fine. So I might have picked an example that's very close to the one that we had in the very close to the one we had, but that's okay. Let's just go through it, and we get the table here, and the pressures are what they are. So we have certain pressures that we're operating this thing over, and which you can see in the table, right? So you can see this thing is giving you all the values. So that's actually, and analyzing this thing is really easy. So known, we'll say heat pump with R134A. What we're going to find, we're going to find the, we're going to find a bunch of stuff. Temperatures at the principal states of each cycle. So T1 through 4. We're going to find the power of the compressor, so W dot C. We're going to find coefficient performance, so alpha. We're going to find, not alpha, I mean gamma. Did I say alpha before? Or did I say gamma? I can't remember. Okay, gamma, right? And D is coefficient performance, so we're going to discuss, compare the results, okay? And we're going to compare. Okay, so now let's do this example. So now let's see, assume. First, we're going to assume that one, it's an ideal heat pump cycle, vapor heat pump cycle. 2, we're going to assume that it's a steady state. We're going to just assuming that kinetic and potential energy effects are neglected for an ideal cycle. All right. It's iced coffee time of year. One of my favorite things. Okay. Um, all right. Let's see. I guess we're gonna do a diagram now. Okay, we can do a diagram. It's not given here in the. Oh, it is. So the system diagram is already. I'm gonna just say um, system diagram. Oops. Could spell. Given. Okay, so the system diagram is given, and it has all the things. We have the work going in the compressor, the condenser, the expansion valve, evaporator. But we're going to make a TS diagram, of course. We have to do that. So whenever you're doing these cycles, you got to have a TS diagram. I guess if you're doing the auto cycle, you can do a PV diagram instead, but I'll ask for the kind of diagram that I want in the problem on the exam. So anyways, we've got a system here. It doesn't say exactly what these things are, but we're just going to assume that it's an ideal cycle because we just already made that assumption, and something like this. So remember that you have to make these things, right? I would really, a lot of you didn't get this totally right on the second exam, this vapor dome thing in the TS diagram. So make sure you get this right. 2, 3, and then remember 4 goes like this way. So actually, I'm going to get rid of that. I'm going to put 4 down here. So 3 is usually right here on the vapor dome, and yeah, so 20 degrees C is got to be in here, and 5 degrees C has got to be here, something like that, right? And let's just put this in a different color. I like orange, so let's do one. Oops, what is going on here? Oh, I had the eraser on. Okay, let's do orange. So 1, 2, and then 3, and then 4 is like this, and then like that. So it's always good to put arrows in on your cycle. Okay, so there's our that's what our cycle looks like. All right, now we're gonna do some analysis here. So we're gonna look for we're gonna use the tables. So for A, we're gonna use tables. In this case, we're gonna use for R134A, which I have in my solution as tables A11 and A12 for superheated and for saturated. So we're going to see state 1. So the temperature, the pressure is 2.4 bar. H equals 244.09. And so we're going to look for saturated. So it's saturated at 2.4. So this is, so state 1. Saturated. So then if we look at this, this is temperature equals negative 5.37 degrees C. So that's this one right here. Okay, that's T1, H1, P1. 2, we know that P2 is higher, so what did I say? It's 8 bar. So, so I know this is 8 bar, right? Yeah, so P2 equals 8 bar. H2 is equal to 268.97, and then we know that S2 is equal to S1 because it's an isentropic ideal compressor, because we call it an ideal refrigeration cycle or ideal heat pump cycle. And so you have those two, and then so interpolate table A12, and you get T2 is equal to 35.72 degrees C, and that's up here. Okay, so way up there. And then you got to come down again for the into the saturated zone. So P3 equals 8 bar. H3 equals 93.42, and this is T3 then is equal to 31.33. And of course for the same it's the same, oops, let me do a circle like I did before. For, we know that this P4 equals 2.4 bar, which is the same as what we had at the beginning. And we know that T4 F4 is equal to negative 5.37, and H4, which is given in the table as 93.42, because it's isenthalpic, right? Kilojoules per kilogram. Okay. All right, so then we've got all these states, and I guess we have all the temperatures. So negative 5.37. Oops, I forgot to put the negative. Yeah, okay, degrees C. Here, and this is degrees C. So it's a little colder, right? 31.33, which is like right here. 31.33, right there. Okay. Yeah, and so that's all the temperatures that you need to find. Okay. Okay, part B. Part B is to find the power into the compressor. So W dot C is equal to, yeah, we have to find the mass flow rate. Well, we know it's M dot E times H, what is it? H2 minus H1. If we want the compressor to be positive, even though it's a negative, it's going into the control volume. But we know, what do we know? I think we know one of the heats. 15 kilowatts. So there's 15 kilowatts. Heat pumps provides a rate of 15 kilowatts. So heating at a rate of 15 kilowatts. So that's QH, right? So we need to find this. So we know that Q dot H is equal to M dot times H2 minus H3, right? Because that's the QH, and then we can find M dot this way because we know the H's and we know the QH. So if we let me just put a here, and we know that M dot is equal to QH dot over H2 minus H3. And then if we put some numbers in here, now this is 15 kilowatts divided by 268.97 minus 93.42. And if we do that math, you get 0.0855 kilograms per second. Okay? So that's what we get for the mass flow rate. Now, if we have that for the mass flow rate, now we can plug this back in. So 0.0855 times H2 minus H3, where H2 is given up here. H2 is 268.97 minus, what is it? H2 minus H1, which is 244.09. Right, and I'm going to run out of room, of course. I should have left myself more space, which is silly. Let's see, so I'll just go W dot C is equal to 2.126 kilowatts. Okay, so you see what we did. First thing we did, we found the mass flow rate, and because we had the heat, we could find the mass flow rate. That's just like one of those kind of investigative things you need to learn how to do with cycles. Okay, look at the things you're given and figure out how to get what you need. Okay, okay, so that's B. C was to find the coefficient of performance. So this is QH, or what am I calling it? Am I calling it QH? Yeah, I'm calling QH. QH dot over W C, and so this, we know this is 15 over 2.126, and that's pretty high. 7.056 is our coefficient of performance. Okay, let's see. Now D, of course, we said that the Carnot is TH over TH minus TC for the heat pump. And this is giving us 293 over 293 minus 278, which is the same answer as we got in the slide example, 19.53. So that's the ideal coefficient performance. All right. So why is this the one that was things with the discussion, and why is this so much higher than the ideal? Even though this is an ideal vapor refrigeration cycle. So I said this is ideal, right? This is ideal. So why is gamma so different than gamma C? Well, one of the reasons is because this is not constant temperature at the top, right? The Carnot cycle would be like maybe at an average. So let me just do this down here. So this is the discussion. I'm going to put the TS diagram here like this. And then what I'm going to do is I'm going to write our cycle in orange, okay? Our cycle in orange is like one, oops, not like that. Like this. 1, 2, 3. Okay, 1, 2, 3, 4, right? Okay, so that's our Carnot. That's our actual refrigeration cycle. The vapor refrigeration cycle for a heat pump, okay? It's the same cycle, right? Heat pump, refrigeration cycle. Now, if I put this one in sort of purple, okay, the ideal cycle would be something like this. So maybe just pick the average temperature here, right? So I'm just going to draw it. Maybe I'll just draw it straight up like this. Okay, so anyway, so this is the Carnot. You can see that there's some area here. It's missing, right? That the vapor refrigeration cycle doesn't have. And that missing area is what's responsible for the poor coefficient performance of the actual, right? So because we can't actually keep an isothermal, so this is isothermal, TH equals constant, and this is S3 equals S4. So technically there would be a some kind of isentropic compressor or turbine in here to get to 4. So 4S, for example, right here. Now, we could do that. It would be a little weird. You could go from 3 to 4S. I mean, so 3. This is 3S, right? If you could possibly go straight across the vapor dome, which you can't do. Okay, so anyway, so 4S, you could actually have an isentropic compressor possibly, or isentropic turbine or something in a vapor refrigeration cycle. The problem is that thing needs to operate in two-phase flow, and this is really watery over here. I mean liquidy, sorry. Like liquid, okay? So you can't have a turbine operating in liquid. It just wouldn't work. I mean, if you could figure that out, maybe you could get a few points of coefficient performance and have a much more efficient system. Problem is that having that kind of having that thing operate in two-phase flow is just not going to work, and it would damage whatever it is, and you would never be able to expand it, and it wouldn't be worth the money. You wouldn't get anything out of it. The efficiency would be poor, so you might as well just put a valve there. Okay. So, anyways, that's the reason. There's more area under the curve there. You get more cooling capability or heating capability depending on how you run it. Okay. So, where are we at time wise? Okay, 30 minutes. So let's do one more thing. One more thing. Okay, so that's the vapor heat pump cycle. Please review it. It's important. It's an important thing to go through. Well, here, let me just get rid of make my slides bigger. All right, now let's talk about one more thing. Let's talk about the Brayton refrigeration cycle. So just like we can operate the Rankine cycle backwards to do a refrigeration cycle, we can operate the Brayton cycle backwards too, using air or gas as a working fluid. So and it's an ideal gas cycle. Okay, so it's not a vapor refrigeration cycle. The working fluids of a vapor compression system undergo liquid vapor phase change. In a Brayton refrigeration cycle, the working fluid remains a gas. And the Brayton refrigeration cycle is the reverse of the Brayton power cycle introduced in Chapter 9 and looks like the following. So essentially, you've got a compressor turbine situation. You've got, instead of constant temperature, they're adiabatic, right? So, I mean, they're adiabatic and isentropic, and reversible, so they're isentropic. Of course, there's maybe realistic behavior, so that's why the dotted line is here in this thing. And you got constant pressure heat exchangers. And so they're not constant temperature processes, but you you've got pretty good cycle here. It's going to be a lot different than the Carnot, but it's going to give you some cooling effect, right? So you run it backwards. You put some heat in here. You put some work rather inside the compressor. You might regain some of the power in the turbine, like what I was talking about, possibly doing the vapor refrigeration cycle. So it goes like this. So the refrigerant gas, which is maybe air or nitrogen or helium or something, enters the compressor at state 1. Okay, and it's compressed. And then gas is cooled by heat transfer to the warm region. So this could be warm region at some TH. The process, then the gas then expands to the turbine to state 4, where the temperature T4 is well below TC. Okay, it's well below the cold gas temperature. And then the refrigeration of the cold region is achieved through heat transfer from the cold region 4 to 1. So here we go. So you drop this thing down through the turbine and you pull the temperature down below the cold region reservoir. Okay, so it's the same thing as the Brayton cycle, it's just backwards. Okay, I've never actually seen a cycle that operates like this, but I've heard about them. Never actually operated one. The Brayton refrigeration cycle, the coefficient of performance, of course, is given the same as it is for the coefficient of performance for a vapor refrigeration cycle, and that is the Q in, which is the temperature from the cold region, which is the room or whatever you're trying to cool with it, into the heat exchanger, over the difference in work. So in this case, it's not just one work, the compressor work, it's work minus the turbine. So the turbine actually gives you some benefit. You get a little benefit by the turbine. It's extracting some work, which you then feed to the compressor and gives you that. So the TH minus TC. So you have to keep the TH below state 3. State 3 is the point at which you have this heat exchanger. So the TH has got to be below there, and the TC has got to be above 1. So you see, there's not much of a difference in temperature between TH and TC. So this may be really only very useful for systems where the temperature difference is not very high. Okay, and that's what we'll probably come to here in the end. Okay, so let's just do an example of it and see how it works. And this will be our kind of final example over the day. Hopefully we don't run over time. So example 2, let me go here. Here it is. Okay, gas refrigeration cycle. The air enters the compressor of an ideal Brayton refrigeration cycle at something kPa, 100 kPa, okay, and 300 K. The compressor pressure is 3.75, and the temperature in the turbine inlet is 350 K. Determine the net work input. So yeah, we got to put work in. We're not getting net work out of this cycle. Per unit mass flow in kilojoules per kilogram. Refrigeration capacity. Remember the capacity. That's the Q in, right? Capacity is what we're pulling out of the cool space. Coefficient performance of an ideal Carnot refrigeration cycle operating over the same 50K. Okay, so let's what color we got here? Okay, so known. So known is the let me get to my right thing here. Okay, so known is is what we have. We know we have here is a Brayton Brayton refrigeration cycle. Okay, we know we find with we'll just say with air. Is it air? Oh yeah, air as the working fluid. Okay, what we're going to find is we're going to find the network. So work in, or just call it work. Well, we're going to call it work net, because the network it's the compressor minus the turbine, right? Refrigeration. So this is Q in kilojoules per kilogram. Oh, we're going to do this per kilogram, right? So we're going to do this little W's. Okay, Q in and coefficient performance. So this is a refrigeration cycle, so we're going to call it beta, and we're going to call this the coefficient Carnot. Right. Okay, so let's do this, and we're going to of course discuss it a little bit if we have time. All right. So now let's see. Assume 1. It's an ideal Brayton Brayton cycle, it means there's constant pressure and isentropic processes. 2 at steady state. Right, cycle, so that means that everything is going constantly. Let's see, then we can find here the diagram. So let's make a diagram. Well, there's 2 diagrams we can make. First, we can make a TS diagram. And then we got to make a diagram of the actual cycle itself. So I guess we'll just make a diagram of the cycle itself first. And that looks like what we just had. So there's a heat exchanger, it's a compressor, and a turbine. They're attached, their shaft is attached, and then there's some work net right there at the control volume. At the outside of the hole, if you take the volume, the system diagram around the entire thing, there's 2 heat exchangers here. So there's a Q in, there's a Q out. Now we got to have some flows that are going around here. I guess we're going to assume this is 1, this is 2. Doesn't look like 1. 1, 2, 3, and 4. Okay. Turbine, compressor. This thing we're calling we just call it heat exchanger. And I guess these are just heat exchangers. There's no condenser, right? I mean, it's not condensing anything or evaporating anything. It's a gas. So it's not doing any of that. Okay, then what we got to do is we got to draw our we can put T1 equals 300 K and P1 equals 100 kPa. We can put our states in the diagram. And there's a pressure ratio. Did we get a pressure ratio? Yeah, 3.75. So this is P2 equals 3.75 times P1. And then T3, are we given T3? Temperature out of the turbine inlet. So T3 is equal to, what is it? 350 K. All right, so that's what we got. All right, now we're assuming that, of course, the heat exchanger operates all the way to the what we call the pinch, where the outside ambient temperature is exactly the same as the inlet of the turbine, right? So we're pinching it all the way to the end of the possible heat that you can exchange. So now the cycle looks like this. So we got like, so we're gonna have 350 here and 300 here, right? And so I got to make sure that 300 is like over here and 350 is like over here. So 350 is here, and then this guy, of course, has to go up in constant pressure. Oops, get rid of that. That was horrible. I think my iPad moved there. There we go. And then this one, of course, drops straight down here, and this one goes like this. So it's going to drop below there. So we got compression in 1 to 2, right? So this is compression. 2 to 3 is the constant pressure. So this is 375 kPa because it's 3.7. This is 100 kPa. Here, constant pressure lines, right? Because it's an ideal Brayton cycle, right? Looks like that. Goes around the cycle like this, and 4. Okay, so the temperature is going to drop kind of cold, right? So you're going to be able to cool this, but the ambient temperature can only be, so 300 is here, so the ambient temperature is like this. So it's very cold, but it can only get to 300 because you have a big change in temperature across the heat exchanger, right? All right. Let's see. So we just put this, we'll just make sure everybody knows that this is Q out and this is Q in. All right, we're done with that. Okay, so now let's do the analysis. Okay, so the analysis is going to be pretty straightforward. So essentially, let's just do the states. So when we did the Brayton cycle, remember, we just find these different states. Find the states. And then since we can look them up in the table, we didn't say it was a cold air cycle, so we have to look them up in the table. We use tables. As A22 is the ideal gas table. So state 1, this is going to give us T1 equals 300 K and H1 equals 300.19. Remember, we're doing H. And you remember why, right? Because it's a steady state, steady flow. I mean, it's a control volume process. So we always use H because it accounts for the flow work. And then PR1 is equal to 1.386 because we're having an isentropic process. So we use PR because that way we can find the second state, because PR1 equals PR2 equals 1.386, and T2 is equal to then, well, I guess we don't even need T2. We don't need T2, we just need H2. So if we need T2, we could find it very easily. So this ends up being 1.386. So P2, we know P2 is equal to 3.75. So then we're going to get PR2. Oh, I'm sorry. That's not right. It's S2 equals S1. Here, let's do this again. PR1, right, is equal to PR2 is equal to PR1 times P2 over P1, right? Because PR2 over PR1 equals P2 over P1 for an isentropic process for S equals constant. Only. Don't use that for a non-isentropic process, but it's very convenient. And so then we end up getting something like 5.198. And if we use the table, we can get H2 is equal to 438.3 kilojoules per kilogram through interpolation on A22. Okay, I'm not going to do it because we're running out of time here at the lecture. Okay, so 3, and you should know how to do it. You should know how to interpolate the tables. It's important. I'm not going to give you too much interpolation to do in the exam, but you're going to have some. So be ready. Okay, T3 we know is equal to 350K, and we can know H3 then directly because H is only a function of temperature for an ideal gas. Remember that. Kilojoules per kilogram. And then we don't know, oh yeah, we need to know PR3 because we're doing a Brayton cycle. So we have an isentropic expansion, 2.7, what is it? 2.38. Okay, so then we'll do the same thing we did for, the same thing we did above. So we know PR4 equals, well, we'll just do PR4 equals PR3 times P4 over P3, which is equal to 2.38. Oops, that's ugly. 2.38 times the pressure ratio, but it's 1 over the pressure ratio because we're expanding, right? Because it's PR4 over PR3, which is 1 divided by 3.75, so pressure ratio, which equals to 0.634. So then we can interpolate again. And we interpolate again in A22, we can find the H. So H4 is equal to 239.9 kilojoules per kilogram, right? And then we have all the H's, which is all we need, right? Which is all we need. So A, the idea, the work output would be work is equal to, let's just do this. Let's just do little w's. Net is equal to the work compressor minus the work of the turbine, which equals to H2 minus H1 minus H3 minus H4 to keep everything positive. So then we're going to end up getting equals 438.3. I'm just going to keep one decimal place, 300.2 minus 350.5 minus 239.9, okay, which ends up giving us a network of network that we put in of 27.6 kilojoules per kilogram. And so if we had the mass flow rate, we could find the kilowatts, right? So if you had 1 kilogram a second per, if you had 1 kilogram per second of airflow through this thing, then you could essentially say that's 27.6 kilowatts, okay? Okay, so the last thing, well, yeah, we have a couple more things to do. So B, refrigeration capacity, so this is Q in, is essentially just equal to H1 minus H4, right? Because it's 1 to 4, right? Right in here, right here, 1 to 4. Okay, so 1 to 4, H1, um, H1 minus H4 is equal to 3, oops, 300.2 minus 239.9, which is equal to 60.29 kilojoules per kilogram. I should put a box around these. These are our answers. Okay. So then the coefficient of performance then, beta is equal to Q in over the work net. Right? Remember, it's the work net because we're getting some work back. We wouldn't want to just count the, we just wouldn't want to count the compressor work. We get some turbine work back. Looks like you get quite a lot actually, 350 minus 240. So that's quite a lot of work that you get back. So you should probably count that in your net works calculation. 60.3 divided by 27.6 gives you a coefficient of performance for 2.19. That's pretty bad. That's an ideal cycle. An ideal cycle is 2.19. We were getting like 6s and 7s with vapor refrigeration cycle. It's not that great. Okay, so let's see. What's the Carnot? In this case, it's TC over TH minus TC. Remember, because it's TC is what we want. And so this is 300 over 350 minus 300 is equal to 6. So there's a big difference, about a factor of 3x. So it's not so bad, but it's probably pretty costly to use this system. I don't know. I'd like to see how it works. Obviously, if you had if you could run this analysis with a bigger temperature difference, you'd see maybe something more difficult to achieve. Because in the end, we didn't solve for this temperature T3 or T2, but it's something like 400 if the H is kind of similar because CP is about 1 approximately. So H2 is going to be around 450. 450K. So it's not too hot. You could probably get away with going higher than that. So I don't know. Maybe it's worth checking out a Brayton refrigeration cycle. But in the end, mostly we don't use Brayton refrigeration cycles. Mostly in any application, there's a vapor refrigeration cycle. Probably because the amount of airflow you require is quite a bit, and a vapor is a lot easier to manage. So with that, I'm done. So this is the end of the lectures. The video lectures are completed, and we've done our lockdown thermodynamics. Hopefully, it's been successful for you, and you've learned something about thermo. I really enjoyed teaching you guys. I enjoyed teaching you guys a lot more when we were together in a classroom. I would have preferred that. But this way, I think that you've gotten some benefit, at least that you've been able to see my lectures over and over again, and they're all recorded, and there's little entertainment there what we threw in as well. So hopefully you enjoyed it, and I look forward to seeing you guys on campus next fall, I really hope, and I look forward to meeting with you again. Please, in the future, stop by and check in with me if you'd like to. So I'd like to see how everybody's doing and keep up with their schoolwork and become mechanical engineers, and hopefully this won't set us back. So good luck with your summer, and I really enjoy it, and good luck with your final exam. I'll be in touch about the format and how that's all going to go, but I think that you'll do well if you study all the material and all the notes that we've given you. So again, I've really enjoyed being with you guys, and yeah, best of luck. Talk to you later.